Okay, so now we're going to take what we learned about the different types of notation, big O notation, big theta notation, things like that, and apply it to code, because we know that those functions will describe the runtime of our algorithm, n squared, n, log n, things like that. Now we want to actually look at some code and see if we can figure out what the runtime is. So the main way we can do this is by using the direct sum method. So this just means we analyze the number of times that each loop runs, and we create summations for each of the loops. And I'm kind of focusing on loops here, but we should really be analyzing every single line of code and seeing how much time that line takes. Most of the time, many lines just take constant time, whether that be a print statement, whether that be a variable assignment, like if I have here int a equals 1, that doesn't take any time to do. That's a constant time statement. But if we have a for loop, we know that we run through it many times, and we want to see how many times do we run it, how many times does the content inside of it run, things like that. So this is our first little example. So we have I going from 0 to n, increasing by 1. Within that, we have a nested for loop. J equals 0, j is less than I, and j increases by 10. And within all of that, we're going to print hello world. Okay, so we can do some brief analysis here. The inner loop, which is this j loop, runs I over 10 ceiling times. And the contents of the inner loop takes constant time. So this print statement takes constant time. How do we come up with this ceiling I over 10 term? Well, let's look at this loop. We always start at 0. That's a great starting point. And we go until we reach I. And we're increasing by 10. So j will go from 0 to 10 to 20 to 30, ... Okay. Now let's just consider random values of I. If I is equal to 24, then j will go from 0 to 10 to 20, and then it'll stop there, because if it increases by 10 more, then it'll go to 30, and this condition won't hold. So here it runs 3 times. What if I is equal to like 37? Then again, j equals 0, 10, 20, 30, and then it stops there. So it runs 4 times. So we can see that we're taking I, dividing it by 10, and if we take the ceiling of it, that tells us how many times the inner loop will run. So let me just get rid of some of this here. This is probably not the best way to do it, but it's all right. And we're just going to notate on the side how many times it runs. So this runs ceiling of I over 10 times. And this outermost loop, well, that's going to run n minus 1 time, or sorry, in this case, n times. And n is like the size of our input, or like what we're doing this analysis in terms of. So this is just going to run n times. We can't really simplify it anymore. So yeah, the outer loop runs n times. So with all of that in mind, we're going to create summations for what we just did. So we'll scroll down here and look at the runtime. So the outermost loop was our I variable. So this goes from really, well, it runs n times. So we're going to sum from 1 to n. And then the inside of that summation will be the contents of that loop, like the cost it takes to run the contents of the loop. Well, within that loop, we had the j loop. So we need another summation. And j ran the ceiling of I over 10 times. So this will go from 1 to the ceiling of I over 10 times. And then lastly, the innermost thing was the print statement, which took constant time. So we'll just put a constant k there. And let's just try to simplify this and see what happens. So we will see that we can ceiling of I over 10, we can like condense that summation into just a multiplication, I over 10 times k. I should probably notate these variables. This is j equals 1, this is I equals 1, right? Since j isn't in the summand, it's only in terms of k here, and k is a constant, we'll just be adding this k ceiling of I over 10 times. So it's just k times that. All right, so we can simplify this a little bit further by saying that this is less than or equal to the summation of I equals 1 to n of I over 10 plus 1 times k. So again, we're being a little bit liberal. We're breaking the equal into a less than or equal to sign, which is, it's fine because we're just trying to find a bound. And remember, the bounds were reliant on inequalities. So the reason why we created this bound is because we don't really like the ceiling function in there. That's kind of annoying to work with. So we can just simplify it to this. And we'll see that this ceiling function will always be less than or equal to this quantity right here. So this is a little bit more pleasant to work with. So let's just distribute that k into our parentheses. And this will be ki over 10 plus k. And then we can sort of break it up into a couple more summations. Do I have enough room? Yeah, let's just do it. So this is equal to the summation from I equals 1 to n of ki over 10 plus the summation from I equals 1 to n of k. Right? Just breaking that summation apart into two, which we can do. And so the first summation, that does have that I term there, but the k over 10, that's a constant, so we can bring it out front. So that will be k over 10 summation I equals 1 to n of I plus the summation from I equals 1 to n of k. So that second summation is pretty easy to solve for. That's just going to be nk. This first one, we're summing from 1 to n of that value I. So this summation right here will be 1 plus 2 plus 3 all the way up to n. So we'll use our formula for that. So that'll be k over 10 times n plus 1 over 2. And then we'll add the nk back in. Simplify this a little bit more. We get k times n plus 1 over 20 plus nk. It's equal to kn squared plus nk over 20 plus nk. And that's like a pretty good simplification right there, because now we can sort of look at this and figure out what the big O notation is. Once again, we want to look for the dominating term here. And the dominating term is this n squared term. These other two n terms, they'll matter for smaller values of n, but once n gets really big, this n squared term is totally going to dominate. So we can conclude that this is big O of n squared. Right? So looking at this code, we said that this is big O of n squared. So that's just saying it's going to run quadratically in time on our input size. So this means that for really large input sizes, for really large values of n, this is going to take quite a bit of time, because the time it takes is proportional to the square of the input size. But for smaller input sizes, it should be okay, right? But really, n squared isn't super duper great, but it doesn't matter. This is just the code we were given. It may be the most efficient way to do it. Probably is. So that is that. Let's do another example. So we have this code here. So I equals n, then we have a while loop, and then a for loop within the while loop. So quite a lot of stuff going on here. So the first thing I like to do is just notate on the side of each line how long things take. So first, setting I equal to n, that takes constant time. The while loop, we'll worry about that in just a moment, but inside of that, setting I equal to I over 3, that takes constant time. Then for the for loop here, that actually works out really nicely because it goes from 1 to n, and both of these values don't change. So this is going to run n times. And then this print statement takes constant time. Okay? So now we kind of want to look at the while loop here. While I is greater than or equal to 10. So I starts at n, and then it keeps on getting divided by 3. So I goes from n to n over 3 to n over 3 squared to n over 3 cubed, and all the way until it's not greater than or equal to 10. So since we're taking a third of it every time, how many times will it take for it to be less than or equal to 10? Well, let's just assume that n is approximately equal to like 3 to the k. Nah. Okay, yeah. So if we keep on dividing by 3, it'll take k times for n to equal 1. So after k iterations, I will be equal to 1, right? And this k comes from taking basically log base 3 of 3 to the k, which is log base 3 of n. So we know that after log base 3 iterations, I will be pretty close to 1. Like, we'll be approaching 1. And, I mean, if you don't completely believe me, try it out for yourself. Take different values of I and consistently divide it by 3. Count how many times this while loop occurs, and it'll be pretty close to log base 3 of n. So this isn't exactly how many times it'll run, but it's a very close approximation. It may be log base 3 of n minus some constant or something like that. I can't immediately think about it. But this would give us a pretty good value of when it's reaching 1, which is, it's less than 10, which is what matters. So this runs approximately log base 3 of n times. So now we can create our summations. So the outer loop goes from I equals 1 to log base 3, because that's how many times it runs. Within that, we have a constant statement. Whoa. Right, this line here takes constant time, so I'll just denote that with a C1. Then we have another for loop, so we need another summation here. J goes from 1 to n, and within that we have another constant, so that would be C2. So this will simplify down to 1 log base 3 of n of C1 times C2n, and that will be equal to C1 times C2 times log base 3 of n times n, and that is equal to big O of n log base 3 of n, or alternatively O of n log base 2 of n, because we're typically using powers of 2 with computer science. So yeah, that is just another analysis right there. So it might be helpful to just notate how many times each line runs, how much time it takes for that line to run, write that off to the side, and then formulate this summation bit by bit and simplify it until you know how to. So that is that. That's like the direct sum method. We can also do a subset or superset method, and this can be a little bit more tricky. The way we do this is we use the superset method to find an upper bound runtime. So that'll be finding like your big O runtime. And the way we do this is we extend the bounds of our loop to nicer values that still contains our range. So sometimes we're not always lucky that I goes from 1 to n, and then j goes from 1 to n. Maybe j goes from 1 to I, and that's like a little bit annoying to deal with. So that's superset method. Subset is used to find the lower bound runtime, so that's big omega. To do that, we truncate the bounds of our loop into a segment that always runs. So this is quite abstract at first, but once we do an example or two, hopefully it'll make sense. So we'll start with this, and we'll start with a superset method. Okay, so what we're going to do is same thing we did previously, in that we're going to notate how long each loop runs. So this outer loop, it goes from 0 to n, so this runs approximately n times, maybe it's n plus 1, but it's O of n. J goes from n down to 0, so that will also always run n times. K goes from 1 to j minus I. So we can say that this is equal to j minus I times, if we wanted to be specific about it. But then it's a little bit tricky, because j and I are always changing, so we don't really have a great quantifier on that. And if we do our summations, it's not super great either. You want to be careful. You shouldn't say that j minus I is equal to n minus n, because that would say that this runs 0 times. There are instances in which it will run 0 times. For example, when I equals n and j equals n, this will say for k equals 1 to 0, do this. So there are times where it runs 0 times, but that's not saying it runs 0 times every single time. So what I like to do for the superset method is consider like the worst case. How many times does this loop run in the absolute worst case? Like, can we find that maximum number? Well, if we're trying to maximize this j minus I quantity, that means we want j to be really large and we want I to be really small. So, inner loop, innermost loop. When j is max and I is min, it will run the most times. Okay? So, I is minimum when it's equal to 0, and j is maximum when it's equal to n. So it'll run n times under these scenarios. J equals n, I equals 0. There's no other possible values of j and I such that this loop will run more than n times. So n is the maximum amount of times it'll run. So what we're going to do is we're going to ignore this j minus I here and just say that this runs n times. We're creating an upper bound on our code here, right? Because it does run n times at least once, we've shown that here, but every other time it'll run less than n times. So we're just going to say that it runs n times every single time. It's an overestimate, but we know we've appropriately upper bounded it. And then if we use the direct sum method, we'll get like I equals 1 to n, j equals 1 to n, k equals 1 to n of some constant c. So that'll just be equal to c times n squared, c times n cubed, and that is big O of n cubed. And notice how we're using big O here appropriately because we found an upper bound for that for the code. Okay, so now we want to do the subset method, and this is where things get a little bit complex. So I'm going to try to draw a diagram here. So we have 0 to n, and we're just going to draw like how the variables I, j, and k are changing. So I starts at like 1, and then on the next time it goes to 2, until it gets up to n. So this is I. Let's use a different color for j. J starts at n, so it's all the way up here, and then on the next one it's a little bit less, until it gets down to 1. And then we have k. So k goes from 1 to j minus I. So what we want to do is we sort of want to it's kind of hard to quantify this or draw it out, but I'll do my best to like explain what we're doing here. K will go from here. Eventually, it's going to get down, j minus I will get very small, right? Because K is dependent on both j and I, but j changes before I changes because j is within I. So this will go down to 0 while this stays 0 during the first iteration. So during the first iteration, k goes from 1 to n, because that's what j starts out as. Then when j goes to n minus 1, it goes from 1 to n minus 1, because I doesn't change, until eventually I goes down to 0, and then k goes from 1 to 0, which doesn't occur at all. So this is sort of what I'm trying to draw here, where this is how many times k runs first. It runs this j times, or approximately j times. Then in the next iteration, it goes 1 less, until it comes down to 0. So that's like in one go of all of this. So now we want to consider what happens when I increases. Well, when I increases, then j goes back to n. So we can think of I equals 1, j equals n. So their difference is going to be like n minus 1. So it's actually going to line up perfectly with the second line. And then in the next iteration, it goes 1 less until it goes back down to 1. So this is all k. And then in the next iteration, it'll line up again with the second line here, and then it'll go down to 1. So it's sort of just, this is sort of just trying to be a visualization of how these variables are changing. It may not help you per se, but sometimes it's nice to see what's going on. But the reason why I want to do this is now we want to like subset our loops into chunks that we know always run. So for example, I goes from 0 to n, always. So I know that it also goes from 0 to n over 2. And I know it goes from 0 to n over 4. Right? I'm quite confident about that. Similarly for j goes from n to 0. So it goes from n to n over 2, right? That's a subset within it. And it goes from n to 3n over 4, right? These are all subsets that I know exist. For k, it's a little harder to quantify because it covers a lot of ground on the first iteration of that inner loop when I equals 0 and j equals n. But then when I increases by 1, we don't get this, we miss out a little bit here. And then as we get smaller and smaller, we're missing out on more and more, right? So what we cover changes as k changes. But I, we know it always encompasses that 0 to n. So if we know I goes from 0 to n over 4, and we know that j goes from n down to 3n over 4, we've already kind of subsetted it. And we know that k loops j minus I times. So how many times is this? Well, we can compute 3n over 4 minus n over 4. That's equal to n over 2 times. Right? In the worst case, when j is at its minimum and I is at its maximum, this will run n over 2 times. Remember, now we're trying to find a lower bound, so we want to find that least amount of times it runs, and here it's n over 2 times. And now we can use our direct sum again. So I goes from 1 to n over 4, j goes from 1 to n minus 3n over 4, because we're counting how many times the loop runs. And then k goes from 1 to n over 2, and the print statement is some constant, which I'll use c. And then when we do this summation, it's just the product of how many times each thing runs. N over 2 times c. This is n over 4 times n over 4 times n over 2 times c. And that's going to be c times n cubed over 32. And that is big omega of n cubed, because c over 32 is just a constant, so we know that it's big omega of n cubed. So if we've shown it's both big O of n cubed and big omega of n cubed, then it is big theta of n cubed. So this subset superset method can be kind of confusing at times. I think superset can be slightly easier because we sort of just are a little bit more liberal with what we do. We extend our bounds as much as possible, so that way they're nicer. Here it's in terms of a constant n times instead of this j and I, where j and I are changing. So we can just extend it however much we like that, up till n. I mean, we could extend it up to like n squared, but that would be a much looser bound. That would give us big O of n to the fourth, which is not false. This algorithm is still big O of n to the fourth, but its n cubed is a much tighter bound. Subsets can be a little bit more confusing, and sometimes just looking at the visual can be a helpful tool, but also thinking about how much of the range is being encompassed by each value and how we can compartmentalize it. That can make things a little bit easier. All right, so that will be that section right there on runtime analysis.